Yes, I'm going to share my screen. Good morning, all. Again, today we are going to run a new subject, which is internal forces under the different loading conditions, actually. We will learn how to draw it, why we need these type of internal force diagrams. We will see that. Let's start here. Let me write here internal forces. Internal forces. Okay. Okay, let's draw an example structural system. Let's draw a frame system here. For example, let's say we have a frame like this. Here we have a pin support, Here we have a roller support. The support types. Okay. On this structural system, we have a few loads. For example, we have a lateral force like this at the top left corner, P1. Let's say there is one more load here, P2 at this point. Okay. What we do first under these loading condition, remember from the support reaction, we always calculate the support reactions first, right? Let me change color. So we will have VA, VB support reactions, and here the point A is a pin support. That's why there will be a horizontal reaction, remember. Okay. Okay. Now we have the system, external loading, P1, P2. We know the support reactions. Okay. Let's say there is a point which is M here. This point is M, point M. I'd like to find the internal forces. Actually, internal forces means under this external loading, there will be some change on the structural system. There will be some external resistance, which makes some, internal resistance, which makes some internal forces inside these columns and beams. So we are going to calculate these internal forces. Why we need these internal forces? Because in the next step, we are going to learn how to design, how to determine the dimensions of these structural members. So to do that design, we have to know internal forces in the system. So we take a look at the internal force diagrams and find the critical locations or maximum internal force points. According to these internal forces, we make the design, we determine the dimensions of the structural members. Here, we have only one point. I'm going to explain the problem on this point M. Here, I'd like to find the internal forces for only this point M. Okay, point M, only for this point. To do that, what we do, we cut the system from the point where we like to see the internal forces. The point is M. We cut the system from point M. Okay, we have this member like this. Here you can see we have HA, VA, At the top corner, we have P1. Okay, this is the point M. Well, we have some internal forces. This is N. I will explain what they are. This is T, and this one is up, back. This is M. So okay, this is the left-hand side of the cut point. Let's draw the right-hand side here. Oh, just a second. Okay, we have this roller support here. Around this corner, we have P2. Okay, we have only vertical B support reaction. Now let's draw the internal forces for this point. This is again point M. Same point, right? We cut the system from this point M. We are gonna have an axial force, a shear force, and let me draw it here, a moment. Okay. So here we have 3 internal forces. Okay. Internal forces are, we have 3 internal forces. One is N. This is axial force. Okay. Axial force. One is T, shear force. And the other one is M, which is bending moment. Okay, we have 3 internal forces, and we always try to find these 3 internal forces, and we always try to draw the internal force diagrams. Today now we are just talking about internal forces on just one point. Today we are gonna learn how to draw the internal force diagrams, which gives us the internal force distribution on the structural system. Okay, we see the big picture, we see every point, and we see their internal forces. So we have 3 internal forces. To solve this problem, our balanced condition, and so this system is in a balanced condition, in equilibrium condition. So we have equilibrium equations, from the statics. We have 3 unknowns, N, T, M, and we have 3 equilibrium equations. Okay, let me write here. For this point, what we write, total X is 0 for the forces, total Y 0, and total M is 0. Three equilibrium So at the end of the day, let me change the color. 3 unknowns, which are N, T, M, right? Solved by 3 equations. Okay. The equilibrium equations are here. So when we cut the system, we can write the equilibrium equations and then find the unknowns. Okay. I'm just, again, I'd like to remind this to you. I'm just talking about to find the internal forces for just one point here, the point M, or any point. You can cut anywhere else. Okay, it's same. I just select the point M in this example. Okay, we have a sign convention to know. Let me open a new page. Yes. Here we go. Sign for internal forces. Okay. Okay, let's say we have a member like this. I'm gonna talk about axial force, shear force, and bending moment here. And I will explain their positive and negative directions. Okay, positive and negative directions. That's why I'm gonna draw 6 members first. Yes. Okay. The first one is N. What's it? Axial force. Let me change color here. Red. Okay. If the axial force, remember, axial force is in the direction of the axis of the structural member. And if the force goes out from my member, it's tension and it's positive. Okay. Goes out. Okay. This sign is positive. We call this tension. The logic is basic. If you apply a tension load to a member, you apply a force out of your member. So the this loading type, these arrows shows us the direction. So all day goes out from the structural member. That's why this is tension. Let's take a look to opposite of this one. If the force squeeze my structural member goes into the structural member, if we squeeze it, it's compression load. It has a minus sign. It's negative. If you see a negative axial force, okay, axial force is axial force. There is no problem. But what you understand, if it's negative, it's a compression force. Okay. If it's positive, it's tension force. Now, this is the shear force, sorry, axial force. I'm gonna now talk about the shear force. T. Shear force. Again, this is positive side. This is negative side. Here, there's a trick. At the right hand side, if the shear force, it depends on our cut direction. We will see in the examples. I'm just gonna show you the directions of the positive direction. Here, if the shear force goes down at the right hand side, it's positive. If it goes up at the left hand side, this is positive for shear force. And the opposite is negative. So if you know the only the positive directions, that's okay for you. Here you can see this is negative and this is negative. You had to know this one. And the last one is, remember, moment, bending moment, M. Eğilme momenti. Here again, this part is positive and this part is negative. Here we go. This direction is positive. This direction is negative. Here, to imagine what the bending moment is, I'd like to show you something. Let me draw. Let's say I have a stick like this, and I have a positive moment on this member. In this system, the start point, I have a curved arrow like this that shows the moment, the bending moment. It shows there is a bending over there. That's okay. The start point of, there is always, by the way, let me draw the deformed shape under this bending. It will be like this. I'm just a little bit exaggerating my drawing, my sketch. After that, I'm gonna explain. Okay. As you can see here, at the start point of the arrow, which is the bottom edge of the member, there is an elongation. So there is tension over here at the bottom line. Actually, I don't memorize it at the bottom line. I take a look to moment. In positive moment, tension is always at the bottom. Compression is at the top. For negative moment, it's like this. Let me draw deformed shape for the negative moment. Here we go. This is the moment here. Tension is at the top. I'd like to explain what is the physical meaning of the positive moment and the negative moment. Okay. At the end of the day, where is my book? Here you can see, let's say this is my book, this is a beam, Under positive moment, it's gonna get this shape, and at the bottom edge, there will be tension at the top edge, as you can see, there is a squeeze over there. It's compression. It's same for the negative moment, like this. Here at the top edge, there is tension in the negative moment, and we have compression at the bottom edge. Here, tension at the top, compression at the bottom. Okay, now we know the sign convention for the internal forces. If we make a summation for this, we draw a sketch like this, basically. By the way, let me change color. That's better. And okay, you can see the positive directions of the internal forces here as a result here. Let me write them T, and this is the moment. You have to know this sign convention while we are drawing or calculating the internal forces. We always use these conventional sign convention. You may ask to me, what is this dotted line at the bottom, which is this, this part, dotted line. This shows the wave direction. Wave direction. We always take into account these positive directions according to this wave direction. In the examples, you are gonna see how we use it. What I suggest you, before you start to any problem to solve, please draw this sketch, this one, the corner of the page, and use this one. I will show you how we use it, but keep this in mind. We use this dotted line. We will see what it is in the example. So it's important to define the positive directions. Okay, it's important to define the positive directions. Otherwise, my positive direction and your positive direction might not be same. This dotted line, in the next step we are going to see, it gives us a common language to us. Okay. Let's do a short example. Let me see. Do I have an example here? Yes, a specific points, specific points, internal forces. I'm gonna solve an example to you. Okay, here we have right here example. Let's see how we use all these data. Let me draw. This is better. Okay. Okay. By the way, can I draw like this? Okay. We have uh, support here like this, and the support here like this. You know, the left support is roller support. The right one is pin support. At the top corner, again, we have load P, and we have a point at the mid of this beam, which is M. Let's write the dimensions here. This height is H. The total span is here, L. The location of this M is here we go, this part. L over 2 and L over 2. So at the midpoint of the beam. Here, the question is, what are the internal, let me write here, what are, or calculate, let me change the wording. Calculate the internal forces at point M. Okay. Okay. Firstly, you know what we are gonna do. We are gonna do the support reactions. Okay, support reactions. What we have again, this point A. Let me write names. By the way, I forgot the important thing. Dotted line here, dotted line here, and dotted line here. These dotted lines shows us wave direction, and according to these dotted lines, we decide the positive directions. Okay, first, let's calculate the support reactions. We have VA here, VB here, VB here, and here we have a horizontal HB. Okay, if we make the support reaction calculation, total by the way, change the color. Total MB equals 0. Let's do it here. P times H plus VA times L equals 0. Here VA is minus P times H over L. Here you can see the direction is this one. Is opposite actually. Let me write here VA. VA equals minus PH over L. Okay, and if we do the same thing for the point A, MA equals 0, VB times L minus P times H equals 0. VB is positive PH over L equals P times H over L. Total X equals 0 for the HB. P minus HB equals 0. Here, HB is P. Now we know all support reactions. We know all support reactions here. Now, what we are going to do to calculate the internal forces at point M here, we are going to cut the system. We're going to cut the system from point M. Let's draw the system here. You can, after you cut the system, you can use left-hand side or right-hand side. It's same. Okay. If you get actually the same, I mean the same here. From left-hand side or right-hand side, you get the same solution if you do the calculations correct. Okay, you're gonna get the same solutions. If maybe you can try it by yourself at home. If you get different solutions from left-hand side and right-hand side calculations, that means you made a mistake somewhere else. Okay, please check your calculations. Okay, let's have a look to the left-hand side. Here we have this. We have P here. This is my wave direction. So what I have a vertical A here, which is minus PH over L. Okay. Yes. Now this is point M. Okay. Before we start this calculation, let's draw the positive directions to the corner to remember what we are doing. Okay, these are the positive directions. Just for a moment. Just for a moment. M, T, N, M, and t. Okay, keep up. Keep this part in your mind. Okay. Now I cut the system from here. Which side I'm gonna use at this point? The point is here. At this point, which side? The left side or right side? The easiest way is, until you get experience, after you get experience, after some practicing these problems, you're gonna see right or left side. You can see here the solid line and dotted line. Take it here and coincide with the where we cut, with the member where we cut. You know, I'm gonna drive it here. As you can see, the solid at the top coincide. The dotted line, bracket line at the bottom, that's okay. So when I look at this direction, that means the cut point is right side of the member. So that's why I'm gonna use the positive directions of the right side. Okay. So here you can see, and I directly draw the positive directions to the sketch. T, M. Okay. Here, what we have directly, if we write the total x, remember to solve. Okay, after we write this one, we cut the system, we put the positive directions of the these internal forces. Then we have, remember, 3 equations, equilibrium equations to solve that. We will one by one apply this. Okay, let's write total x is 0. And the x direction, what I have here, I have p minus n, sorry, plus n. They're in the same direction. P plus n equals 0. So axial force at this point M is n equals minus P. This is the first internal force of point M. The second one is total Y equals 0. Okay, in the vertical direction, what I have, which goes up vertical A, its magnitude is negative, that's okay. It's in the positive direction, minus PH over L. Okay, so is there any other vertical load on the system? Yes, at the point M, we have T that goes down in the negative direction, minus T equals 0. Okay. If we take this T, the other side of the equation, T equals minus P times H over L. This is the second internal force of point M. Okay. Now, what we're gonna do here, we will calculate the total moment at where? At point M. Here. At this point. Let's write the total m. I have a moment here, or let's get started. This is the rotation point, vertical a times distance. The distance is L/2, remember. Let's write the equation here. Minus ph/L times L/2. Okay. This turns the system in this direction. At point M, we have a moment, ready moment, which is our internal force, turns the system in opposite direction. So it's minus M equals 0. If we take this M, the other side of the equation, what we are going to see here, M equals, this goes, minus P times H/2. Okay, now we have just completed to calculate the internal forces at point M. Point M. But what we did, please keep in mind this. Here, we have just calculated the internal forces at only one point, which is point M. Okay, we are not calculating the internal forces all around the structural system. We are just doing this calculation for point M. Okay, let's write the rules. Okay, you know what we did, but I'd like to write the rules for 1 point internal force calculation. Let's jump to another page. Okay. Here we go. If we want to calculate the internal forces for any specific point, for any point, okay, what we do, firstly, cut the system from the point where we want to get internal forces. Okay, this is the first rule. Okay, put the positive directions of the unknown internal forces. Put the positive directions of the internal forces to be calculated. Right? And write the equilibrium equations. for NTM. Okay, if you follow these rules, actually, you can calculate this internal forces for a specific point. Okay. Here, yes. Let me take my notes. Okay, we have mainly. By the way, any questions so far? Any question, comments, anything else? No, I think. I just want to give a brief explanation regarding the isostatic and hyperstatic systems. Okay. I guess we talked about this isostatic and hyperstatic systems in the statics course in the previous term, but I'd like to remind you again what they are. If we can solve the support reactions and internal forces with the equilibrium equations, with our three equilibrium equations, that system is isostatic system. So we can make easy calculations. If we can't do this, the system is hyperstatic. Okay. Okay, we have some methods to solve the hyperstatic systems by hand. If it's a simple system, yes, you can do it by hand. But if you have a complex structural system, it's not easy to do it by hand. We use softwares. We use computer to make these complicated calculations. Let me write what I said again. Isostatic versus hyperstatic systems. If all support reactions and internal forces are calculated by using equilibrium free equilibrium equations, this structural system is isostatic system. Okay. Let me give you some examples. You know, the simple beam, you know well this one. You have pin support and roller support in each side. You may have frame systems like this. Again, roller support at the side. Pin support. It may be a cantilever system. Cantilever is always isostatic system, cantilever. It may be a beam system like Okay, this is the Gerber beam. It has internal hinge here. This is cantilever. Here is a frame system. Here is a simple beam. These are the examples for isostatic system. Okay, this is isostatic. Let's talk about a little bit the hyperstatic system. To solve hyperstatic systems, we need equilibrium equations and geometric compatibility equations. Geometrik uygunluk denklemleri. Geometric compatibility. Okay. The hyperstatic systems is not subject of our course. This is a general knowledge for you. In the civil engineering department, we always teach how to solve these hyperstatic systems by hand, but you don't need to do this. That's why I'm not gonna explain that. But if I'm gonna give you some examples, for example, if I give you a beam with double pin support, if I have one roller support, it's gonna be simple beam. But here we have, vertical support reactions and horizontal support reactions. This is a hyperstatic system. Let's have a look at frame system. Instead of one pin, one roller, if I have two pin supports, again, I'm gonna have vertical and horizontal reactions. I may have, for example, an arch. Here I have fixed support. Here I have fixed support. Again, these are the examples for the hyperstatic systems. Okay, so as you can see, take a look to, for example, let's have a look to first beam. How many unknowns I have? 1, 2, 3, 4. I have 4 support reaction, but at the end of the day, I have 3 equilibrium equation. So I can't solve for unknown with 3 equation. I need extra one more equation. So here we use geometric compatibility equations. It's same for the frame. You can see 4 unknowns, and we have 3 equations. Let's have a look at the arch here. It's at the fixed supports. This support type is fixed. We have we have 3 unknowns. Sorry, 3 on one side, 3 on one side, totally 6 unknown. 6 support reactions we don't know. 6. But how many equation we have? 3. So there are 3 missing equation. That's why we call this type of 3-degree hyperstatic. 3-degree hyperstatic. We need 3 compatibility equations to solve this one. Okay. This is a general information for the hyperstatic systems. What we learned so far, we learned how to calculate the, we learned what the internal forces are, what are the sign convention, how we can calculate the support reactions on a specific point, not all the structural system, on a specific point. And we did an example. Then we talk about the isostatic and hyperstatic systems. Okay. Now, okay, we will learn to draw internal force diagrams for a structural system, to for the whole system. Okay, what we did so far, we only calculated the internal forces for one point, for just one point. But okay, in specific problems, we can wonder the specific points internal forces. But generally, to make a design, we want to see the big picture. We want to see the internal force distribution on the structural system. To do that, we have to draw the internal force diagrams. Okay. Here we go. Now we are going to learn how to draw it. Okay. Right here. Okay. Internal force. Internal force diagrams. Okay, what is this internal force diagram? Again, I'd like to explain the problem with a simple case. I have a simple beam here. I have an external loading like this on the beam. And I have point M again. Okay, what we did so far, actually at the beginning of this, at the beginning of today, we calculated the internal forces at point M. Okay, if we calculate at point M, what we have? Oops. Sorry. At point M, I have axial force, shear force, and moment. This M shows us the point, okay, for us. But if we do this, if I calculate the internal forces at each point of this beam, I get the internal force diagram. For example, let's say the internal force diagram. This is an example. is like this. I don't know. So here, this is the point M. So far, I have just calculated these forces, TM and MM. If I do this calculation for each point, I get this curve, as you can see. So this is the internal force diagram. But what we are gonna do, we are not gonna cut the system from each point and make this equilibrium equations. We are not gonna write the equilibrium equations for each point. There are some methods to draw these curves. So I will explain them to you. So we will learn to draw this. This is the internal force diagram. I'd like to give you information about the sign convention of this internal force diagram. Let me change color. Of internal force diagrams. After I explain this part, I'm gonna give a break. Okay. Sign convention of internal force diagrams is change color. Okay. Oh, by the way, no. Okay. While I draw these internal force diagrams, what I have: moment, shear force, axial force. So according to my viewpoint, the upper part of the moment diagram is always negative. Bottom part is positive. Okay, for a moment. This curve is just an example, but what I'm trying to explain, if I draw a line or a moment diagram, this is my viewpoint, wave line. The bottom part is positive. In moments, bottom part is always positive, top part is negative. For shear force and axial force, the top part is positive. Let's say I have a curve like this, shear force diagram like this. This is T. This part is positive. This part is negative. Why this is important? At the end of the day, okay, you know the you can calculate the moment values or shear force or axial force values. If you combine them in a internal force diagram, we have to use these sign conventions, these rules. Why? These are a common language between the engineers and architects in global world. Okay. If you don't if you change the signs, we can mix everything to each other. That's why to speak in the same language, we have to use these sign conventions. If I have a axial force, I don't know, let me, this part is positive, this part is negative. Okay, these are the positive directions of the internal forces. In the examples, you're gonna see how we use these positive directions. Okay, these signs can be seen meaningless at the moment. That's okay. But keep this in mind, there's a sign convention. At this point, maybe you have to know the sign convention. You must know this one. But now, at the moment, you don't have to memorize it. Just try to understand how we use these signs while we are drawing the internal force diagrams. After that, while you are doing practice, you can keep this sign convention in your mind. Okay. Okay, guys, it's 10:15. Let's have a break. We're gonna be here at 10:45. Okay. See you guys. Share screen. Yes. Okay. We have just started the internal force diagrams. And at the end of the first session, we learned the signs of the internal forces, moment, shear force, and axial force. Okay, let's go ahead. Okay. There's a relationship between the shear force and the moment diagrams. I'm gonna talk about this subject here. Relationship between shear force, which is T, and bending moment. Bending moment, which is M. Okay, here we have a beam. Let me draw a good. Okay, this is my beam. Here we have roller support and pin support. On this beam, I have an arbitrary distributed load. Okay, let me change, by the way, color. Okay, we have a distributed load like this on top of the beam. We call this one is QX. QX. Okay. Here, if we cut a piece from this beam and take it out, let me show you how. Here, from this support, from a distance which is X. Here, the length of this small member is dx. I'm going to take out this portion. The total length of the beam is L. Okay. I'm going to take out this portion. Okay. Let's draw it here. I have. This is the side view. You can see we have a side view of beam. I take out this red portion here. Again, here, this is the side view of the beam. On the beam, we have distributed load here, which is QX again. And the length of this member is, remember, it was dx. It was dx. Now, here, this is the axis of the beam. Let me change color. What we have a shear force here and a moment at the left-hand side, as you can see. At the left-hand side, at this section. After dx, we are going to have a shear force here, but it's a little bit different than the left side. It's going to be t plus dt. Okay. There is a differences between the left and right hand sides. It's same for the moment. M plus dm. Why we have these differences? Because there is a distributed load on top of this portion. As you can see, QX, we have this QX here. So that's why, due to this QX, the left-hand side and the right-hand side shear force and the moment are different. Okay, are different. If we write the equilibrium equations on this beam portion, let's write first for the shear force. T at the left-hand side, we have T, which goes up. At the right-hand side, we have T plus dt, goes down. So they're in opposite directions. We can write here T minus dt. Okay. And on top of the beam, there's a uniform distributed load. It goes down. So it's Q times. Remember how we convert the distributed load to the point loads. The magnitude of the distributed load times length. Q times dx. Okay, equals 0. Here, what we have we cancel these two. At the end of the day, dt over dx equals minus q. Minus q. Uh, let me dt is here. Minus q minus q dx. Okay, as you can see here, at the right hand side, we have t plus dt here, as you can see. What does this mean? If I know this is actually is t minus q dx. What this shows to me, if I know the shear force at one point, for example, here at the left-hand side, then I can reduce the external loading. Then I can get the right-hand side shear force without any specific calculation. I know T, so there is a QX at the top. It's an external force, sorry. T minus this external loading, this part is the external loading. Loading. This gives me the shear force at the next point, which is here in this example, right point, right side or. Okay, we will use this rule in our calculations. If we know the shear force at one point, that shear force minus the external loading in between the next point gives us the next point's shear force. This is the first rule to know. Okay. This equation is for the, by the way, what we did here, we write the total y equals 0. Let's take a look. Let's take a look the next page. If we write for the same portion of the beam, if we write the total m equals 0, okay, we are gonna write m minus m dm, then plus q dx square over 2 plus t dx plus dt dx equals 0. At the end, what we are gonna get, dm over dx equals q. So here, if I change the locations, q dx, let's take the integral of both sides. X, we will see m is q dx. Oh, by the way, I made a mistake here. This is not q. I'm using t instead of q. Sorry. Okay, what I understand from this equation, this is the second equation. By the way, the first one, go, let me go back. This is the first equation. Okay. What we understand from here, uh, integral means the area calculation, basically. You might know this one from the high school knowledge. According to this second equation, if I have a shear force diagram, T diagram, if I calculate the area of this shear force diagram, I can I can draw the moment diagram easily. So what I'm gonna do, I know the moment at the start point. I have the shear force diagram, calculate the area on top of the existing moment and get the uh, resultant moment value. This is the rule. We have two rules. We calculate the shear forces depending on the external loading. We remove the external loading from the shear force. Shear force, the start point's shear force minus external loading gives me the second point's shear force. We will see how to use these rules, okay, in the examples. But I'm just repeating the same sentence to keep in mind. If I have the shear force diagram, I can calculate the area under this diagram and add this area to the start point's moment and get the other points moments. So we will use this method in our calculations. Okay. To draw the internal force diagrams, I'm gonna give a chart for you, which helps while you're drawing the internal force diagrams. Let me write the table, the relations between among and by the way, this is not n, p, t, m. Here p is external loading. Okay, this is the load. Let me write the load. I'm gonna draw the table now. Load, which is P. The shear force, T. Just a second. Load, P. Shear force, which is T. And bending moment, which is M. Okay. if there is no load in some portion of the beam, let me write, if the load is 0, the shear force diagram goes constant. Okay, it's constant. And bending moment will be first degree curve, which means linear. Okay. If I have a uniform distributed load, okay, the shear force diagram will be first degree, means linear. The moment diagram will be 1 degree up. Here, second degree. Increase the shear force degree and get the bending moment. If I have a triangular distributed load, I'm gonna have second degree curve and third degree moment. If I have a second degree parabolic distributed load, the shear force will be third degree curve, and the bending moment will be one more greater than the shear, fourth degree. If there is a point load, by the way, let me put the lines between the rows. If I have here a point load, there will be a sudden change on the shear force where the point load acts on the beam. Sudden change. On the shear force. And if shear force, last line is somehow, if shear force is 0, moment gets maximum or minimum value. So this means if we are looking the maximum moment, we should look for the 0 shear force on the structural system. If we find the zero shear force location, calculate the moment at that point, it gives you the maximum moment value. Okay. Okay. Let me see. Oop. Here's an example here. By the way, next week is the application week. We are gonna show many examples regarding this issue, these subjects. That's why I recommend you to attend the class next week, especially. We are gonna apply all this data today. I'm spending my time while explaining the concept, but the application is also important. So please try to join class. Okay, this is the table you have to know. Okay, let me put here call. Okay. Oop. This table is important. We will see how we use this table, but this is important. Okay, I will draw some examples to show what we said on this table. For example, if I have a beam on this beam, I have a distributed load, uniform distributed load. Okay. Here, and I have a P. This is P is uniform here. Okay. Uniform distributed load. If we draw the shear force diagram of this system, okay, we assume that we know the shear force at this point. So you can see from this point to this point, there is no shear force, there is no external loading. The P is zero, the load is zero. Let's say my start point, the shear force is this. From here to here, my curve goes constant to this point. And now I have a uniform distributed load. I'm at this point to the end of, this is the end of distributed load. This is the start point. So if I have a uniform distributed load, remember, if we go back to table, here the shear force diagram is first degree curve, which is linear. I will have a linear shear force diagram, but remember, I know the shear force at this point minus the external loading gives me the shear force at this point. Let's assume that we did this calculation and shear force value is this. How I'm gonna connect these 2 points with the first degree curve, or I mean with a line, because it's gonna be linear. Okay, this is a line. Then from this point to this point, there is no external loading, so shear force goes constant like this till this point. Oops, sorry. And here I have a point load. Point loads. What I said regarding the point load. If I have a point load, there will be a sudden change on the shear force diagram where point load acts. Okay, take a look here. P is here, and there will be a sudden change. I will go down, and after this point till the end of the beam, there is no external loading, and it's gonna be constant. This is line. Okay, so this change is here on the shear force is P. I tried to show you the how we apply the table to the curve. Okay, this is the T diagram. Let's do the moment diagram. Okay. Again, these are the oops. These are the critical points. I'm gonna use another color, for example, green. Okay, at this point, let's say I have a moment, a start moment here. Okay, we don't know this one, this point. This is not important for us at the moment. Start. How we can go to the moment diagram from shear force diagram. We're gonna calculate the area and add this part. By the way, the top part for the shear force diagram is positive. The bottom part is negative. Don't forget this one. You can see here we have a constant shear force diagram. That means moment diagram will be linear. This is linear. Let me write here, first degree. After this point, as you can see, I have a linear first degree line at the shear force diagram. So for the positive part, I'm gonna go, by the way, this point is important. I'm gonna go up to here, and then this area is negative. Let me clear here, just a second. Okay, this is the first degree. Moment is 1 greater than the first one. That's why here is second degree curve. Here is second degree curve. After that, as you can see here in this portion, there's a constant. So that's why the moment curve will be linear, first degree. And again, this portion is also constant. The moment diagram will be linear. Linear. By the way, let me clear and make correct this part. First degree. Okay, this is the moment curve. This is the moment curve. Uh, Here, I didn't give any number, anything else. I'm just practicing how we are using the table to draw this type of shear force and the moment diagram. Okay, it looks complicated at the beginning, but you have to do more practice. Otherwise, it's not easy to do or solve these problems. It looks simple, but when you get started, you will see you can't do that. So you're gonna go back to take a look at your notes and then solve it. By the way, there are many examples on Google regarding these or in YouTube, whatever. You can use these references to study. Uh, but please make some examples, okay, before you come to class. Next week, I will do examples, not this week. This week, I'm gonna just explain the concept. Uh, let's do another example like this. I'm gonna show you again how we use the table. If my loading is like this, uniform distributed load, here I have a point load, a uniform distributed load here. Yes, this is P1, this is P2. These are uniform distributed loads. Here I have a point load like this. This is the shear force diagram. This is the moment. Oop. Okay, here, let's say my shear force at the beginning is this value. In this portion, there is no external loading from here to here. The curve is constant. Okay, curve is constant. And then let's say from, let me draw these critical points. Okay, here I have a uniform distributed load, shear force minus external loading gives me the shear force at this critical point. Let's say I reduce the shear force to this point, but how I'm gonna connect these 2 points? If the load is uniform distributed load, shear force curve will be first degree. I mean, it's gonna be linear. It's gonna be a line. Right? Good. Now I'm at this point. I'm under the point load. So remember, if there is a point load, there will be a sudden change on the shear force diagram. So I'm this point minus this external loading. It's gonna be maybe here, this point, but I'm gonna connect these 2 points with a line, vertical line. You can see at this point, there is a sudden change. The shear force drops down from this point to this point due to this point load. After that, I have here distributed load, uniform distributed load. Again, the load shear force at this point minus the uniform distributed load. Let me put the point here. The shear force will be here, and connect these two points with line. Okay, this is the first degree. This is the first degree. After this point, there is no load on the structural system. So it's gonna be constant like that. Okay, if we draw the moment, this is the shear force diagram. Let's transfer the critical points to the moment diagram. Okay, I'm gonna change color. Yes. Let's say start moment is this. We don't know what it is. At the beginning, there is a constant part. So, by the way, for the first example, this was the positive part. This is gonna be here. And here. This is first degree. And now I'm in this portion. The line is first degree. Calculate the area at this point. And if this is first degree, increase the degree 1. It's gonna be second degree. Okay. And then here also a negative area, because this part is positive, this part is negative. The curve heads up now after this point. Goes here. This is again second degree. And after this point, the shear force is constant. Then it means it's gonna be linear. So this is first degree, totally positive. By the way, I must remember something here for both of these examples. Let me change the color, for example, to the purple. In the first example here, when the shear force goes from the 0, this point is M max. Okay. It's same as for the second example. My shear force diagram goes from 0 at this point, and I will get the maximum moment at this point. Okay. Keep this in your mind. Okay, what we have more? Actually, I'm not gonna solve any example today. Today, I just tried to explain the concept. I'm done for today. I will solve examples next week. As I said before, I strongly recommend you to join class next week to see. Okay, now I'm just talking about concept, how we draw the curves, but these are examples without any number to explain the concept. But in next week, we are gonna do some examples with numbers. We will calculate the shear force values and moment values, and then draw the curves. That's why please join the class. That's all for today. I hope to see you again next week. Take care of yourself. Have a good weekend, guys. Okay, bye-bye.